Hey guys, today we'll be talking about electromagnetism. Unlike other phenomena that we see, inertia and momentum, electromagnetism can be a bit tricky for you to understand, mainly because you don't get to see it. Alright, so before we go into the details, let's first see what magnetic field is, because that's the most important thing in this topic. Alright, a magnetic field, as per definition, like you can see at the back, okay, is a region, or rather an area where magnetic material or a current carrying conductor, basically a wire carrying electricity, experiences the force of magnetism. Okay, what is this force of magnetism? For us, it's invisible to the human eye. Okay, we can't feel it either. You put your hand near a magnet, you don't feel anything. But the field line is there. You would have seen drawings in your books such as this, North Pole, South Pole of a magnet. You'd see the field line leaving the North Pole and entering the South Pole. Okay, everything enters through the South Pole, everything leaves through the North Pole. Alright. In reality, there are hundreds of thousands or rather millions of these lines depending on the strength of the magnet. So whenever a magnetic material, which is one of these three, iron, cobalt or nickel, goes near this magnet, it experiences the force. For example, we're going to look at a demonstration here. What you can see here is a permanent magnet, and this is an iron screw. Alright. See, when they are far, it cannot experience the field. But all I have to do is bring it nearer, come a point, you see that attraction happens. I did not push it, that was the magnetic force. Alright? Electromagnetism is the interaction between magnetic fields and electric fields. So what is this interaction we are talking about? Like we've learned before, around a magnet there is a field, a magnetic field. Similarly, around a current carrying conductor such as a wire like this, if I fix it to an electrical source, it will have electrons moving inside, which creates a current. Okay, and this in turn generates a field around it. So when this magnetic field and this electric field interacts, it creates a force. Alright? Okay. So using this principle, we can create electromagnetism, DC motor or electrical motors. Alright? A simple demonstration of an electrical motor. Okay. What I have is an iron screw stuck to a permanent magnet. Okay. Now I'm sticking this iron nail to the bottom of a battery. I'm fixing electrical wire, and if you can see, as soon as the electrical wire touches, the magnet starts spinning. Alright? This is because the interaction between these two fields has created a net force, and this force has caused the spinning. So this is a simple demonstration of how a DC motor works. Of course, there are more structures to a DC motor which we are not discussing here today. There are two main types of magnets. One is a permanent magnet. This is always magnetized and it doesn't require an external energy source. This is usually made from materials such as alnico or ferrite, placed in a very strong electrical field. So that's how this permanent magnet is made. Alright. Today we are talking about electromagnets. Electromagnets are basically made by a conductor coiled around a soft iron core. Alright. So what is this purpose of this soft iron core? Like we've discussed earlier, whenever a conductor carries electrical charges around it, it creates a field. And by having an iron core in the middle, it focuses all of the field, and now we get an electromagnet. Okay. The simple demonstration is this. What I've taken is an iron nail and coiled copper wire around it. Now as you will see, I will connect it to a battery, typical AA battery, and you see it can now lift this paper clip. Alright. If I were to do this without this energy source, nothing happens. No attraction. So this shows how the flow of electricity in the wire creates a field, and that field has been focused by this iron core or this iron nail, and now this acts as a magnet. So the principle how we get to this is two material. One, as we can see, is the soft iron core, and the second is the solenoid itself. Alright. Now let's look at a solenoid. Solenoid is a fancy name given to basically a cylindrical wire. Alright. For example, I'll show you how a solenoid is made. You have a straight wire, you have a cylinder like this, you just coil it around this. Alright. Now if I remove this, what I have now is a solenoid. Alright? So why do we do this? The moment you've coiled it, the field is more focused. Alright? And if I connect this now to a power source such as this battery, okay, it can start acting like a magnet. Because why? For the same reason, the electrical fields have been focused. Alright? So we'll look at the definition now. Solenoid, a cylindrical coil of wire acting as a magnet when carrying current. It can only do this when there is current. So that is how an electromagnet is made. So you would have read that there are many advantages of electromagnet, primarily because you can switch it on and you switch it off. When I connect it to a power source and it's a magnet. When I want to drop something, I don't want it to be a magnet anymore, I simply let go of the power source. Okay, your question may be, why use an iron nail? Why not an aluminium nail, or why not a steel nail? Alright? Aluminium and materials such as gold and copper cannot be magnetized. Only, like I mentioned, these three materials can be magnetized. And we choose iron over steel because steel has a tendency to retain the magnetism even after. So imagine a scenario in probably a junkyard where they're trying to lift iron and then drop somewhere else. If you were to make it using steel, when you switch off, it will not let go. It will let go after a while. So that's not desirable. So that's the primary use why we decide to use iron nails. Alright? Okay. So that is the basic lesson of how electromagnetism is done. Solenoid and an iron core. Using both, you run a current, you get magnets. Alright? And the next part in solenoid is determining the polarity of the electromagnet formed. Alright. We know electricity flows from positive to negative terminal. Alright. Using the right hand grip rule, we would be able to determine the polarity. Okay. How does this work? The four fingers determine the direction of the current flow. And the thumb, wherever the thumb ends up pointing, is the north pole. So if I'm pointing like this is the north pole. If I'm pointing like that is the north pole. Alright. Now, imagine if this was connected to a positive terminal and this was connected to a negative terminal. Let's flow the sequence. Now, the current flows through this, circles around, and it exits here. Alright. So, all you have to do, using your fingers, follow the current. Can you see? It grips around. That means it goes around in this direction. Alright, clockwise if you were to view from this direction. Alright, so now I have done that. I just hold my thumb out. So from this I've learned that this is the north pole. So very simple, follow the current, grip it according to the direction of current flow. Where your thumb is pointing, that is the north pole direction. Alright, so you would have seen drawings and such. So all you have to do when you look at a drawing like that, just use these fingers, follow the direction of the current, wherever your thumb is pointing, that is the north pole. So that is how an electromagnetic poles are detected. Right. For further in-depth discussion of this topic, or to look at questions or techniques of answering questions or figuring out what are the kind of questions that always are being asked in SPM or IGCSE, join us for our regular classes at Ignis Education. Thank you.